next part, before going on to understand about the different types of the stress and the strain relationship, we should understand about what is the thing that can be understood or can be inferred from the stress strain curve about the toughness of the substance. Whether a substance is tough, whether the substance is brittle, whether the substance is ductile or not, that we should be able to understand and comprehend from the stress strain curve. So in this part of the chapter, we are going to discuss about the stress and the strain relationships for the different types of substances that we know of. So students, we have understood a lot about the mechanical properties of solids so far. So we'll now go further to the part 3 of this particular topic. We'll now try to understand how the proportionality constant that we have defined can actually be related to the different types of objects. So let's start off with a one-dimensional force. That is, when we apply the force only along a particular direction, and that results into the different kinds of deformations. The first of all is what is known as a tensile or compressive stress. So tensile or compressive stress, so in this particular case, either you compress it or you extend it, right? So in either of the two cases, the force is going to be applied perpendicular to the area. So this becomes F by A. In the same way, if we try to define about the longitudinal strain. So longitudinal strain, so because of the tensile or the compressive stress, there is going to be a strain also produced. So the amount of strain produced is going to be defined as delta L divided by L. So this is the change in length produced because of the application of the force per unit area. Then we define something known as the Young's modulus. So Young's modulus is Y. So Y is, we have already defined this. So if we have to define understanding about it more, so how do we define it? So Y is going to be equals to the force per unit area divided by the change in length per unit length. So this is how we define Y. Let's try to elaborate further by looking into it. So we have, this is our object. You effectively apply the force per unit area, so that is represented as P. So if you apply the pressure, so as a result, there is going to be, this is going to be the thinness that is going to happen, and so you will get something known as a strain. So the length of this object is going to increase, right? So when the length increases, originally the length was L, final change in delta L, so that results into the strain as delta L by L. Further, if you would like to look at it, that originally it was L naught, so finally the strain is going to be equal to delta L divided by L naught, right? So this is what we have. Then if we go further, we'll talk about something known as the Young's modulus. Young's modulus will be equals to the tensile stress divided by the longitudinal strain. So what is going to happen here? So we'll say that Y, which is equals to force per unit area, divided by the change in length per unit length. So this can be written as F into L divided by into delta L. So this is how we define the Young's modulus. Now the Young's modulus will have the same units as that of the stress. So if I talk about the different types of material and what are the values that they have. So for the first type, let's say mild steel. So mild steel has Young's modulus per gigapascals, that is 210. Copper has 120, bone has 18, plastic has 2, rubber has 0.02. So as you see, as you go down, the Young's modulus value is decreasing, and therefore their elastic limit also is decreasing, right? So the metals, as you see, will have a much larger elastic moduli as compared to the non-metals that you have. Okay, now let's try to go into a two-dimensional framework. So this is something that we have already discussed. So in a two-dimensional framework, what you see is this: you apply a tangential or a shearing stress. So if you apply a tangential, so this is your tangential force that is being applied. So as a result, there is going to be a tangential stress that is produced. So stress is going to be equal to force per unit area and the shearing strain. So if I say that theta is this angle, so like here theta is the angle that has been there, so that results into the extension as delta x. So delta x is the extension produced. So the extension is delta x divided by L, so y or L, however you will have to write it. So that is going to be equal to tan theta. So this is what we get. Further, if we talk about the elastic moduli, in this case, so elastic moduli is also known as a shear modulus. The name given here is shear modulus. So shear modulus is also known as the modulus of rigidity. So how will you define it? So G is going to be equals to F by A divided by delta x divided by L, or you can simply say F divided by A tan theta. So this is the expression of the tangential or the shearing stress that you have. Now let's move on. Let's take the case of water filled in a container, maybe a ball, water filled in a ball or water filled in any other vessel. So in this case, what's going to happen? The water is going to exert force to come out. So if it exerts force to come out, so effectively the force per unit area acting in this case is going to be outside, means along all possible directions, right? If it is along all possible directions, that is where we define it to be something known as the hydraulic stress. So hydraulic stress, that is more related to the water, that's a kind of the external pressure. So the pressure that the internal water exerts outside is something that the object also keeps it inside. To keep it inside, you need to apply some external pressure. So the object keeps the pressure intact. So hydraulic stress is going to be equal to the external pressure. And since this acts on all possible directions, we refer in terms of the pressure itself. Further, there is something known as the volumetric strain. So volumetric strain, here obviously there is going to be change in volume occupied, change. So that is what is defined as delta V divided by V. Further, if we talk about elastic moduli, so elastic moduli in this case is known as the bulk modulus. So hydraulic stress is generally created by keeping an object in a fluid. So if we keep an object in a fluid, that is going to result to a decrease in the volume. So to keep the moduli positive, you basically take a negative sign. For instance, let's take any ball, okay, a kind of rubber ball or a plastic ball, and you take that ball and put it inside water. The ball is going to shrink in volume, right? So its volume is going to decrease. So when its volume decreases, because the water will try to push from all sides. So when the water tries to push from all sides, as a result there is a change in volume. So what happens in this particular case, if we love to call in this case as the bulk modulus, so the bulk modulus in this case is going to be equal to the pressure divided by minus delta V divided by V, or you will say minus PV divided by delta V, right? So this is the bulk modulus in the case of water, or when the liquid is surrounded or the object is surrounded from all sides. So the pressure is being exerted from all sides, right? Okay, so if we just try to understand it, so this is the expression that we get. The expression that we get is force per unit area divided by delta V by V. So volumetric strain is going to be defined as delta V by V, and the volumetric stress is force per unit area. So this force is going to be there along all sides, so the pressure exerted is going to be along all sides, right? So this is what we get in this case. Now the typical values of the elastic moduli go here. These are just for your information that tungsten has this value of Young's modulus, shear modulus is this, and bulk modulus is this, and similarly you can figure out for all the things. Mercury, because it exists in a liquid form, so obviously has bulk modulus, it does not have the shape and size, so therefore we do not have the Young's modulus or the shear modulus, right? So these are the typical values that you have. Now we already understood about the stress strain curve, right? So in the stress strain curve, what did we see? That there is a elastic limit, there is a plastic limit, there is a fatigue limit and all. So at every point there is a significance. Up to the elastic limit, what you see is that the stress is proportional to strain and so on. But that stress strain curve can also vary from one object to other, right? There can be some objects which are very, very ductile, that is, you can extend it. There are some objects which are very brittle. So for the brittle objects, the stress strain curve, that particular slope is going to be smaller, or that particular length is going to be smaller. If you talk about the stress strain curve for the case of a ductile object, that length is going to be longer, right? So if we have to identify it, so this way you see that. So this is basically engineering tensile stress, engineering tensile strain that you are very much what you need. So this, if you define it, so here you have a smaller percentage EL. So EL is what? That is the final length minus original length divided. So basically the change in length divided by the original length. So how much is the percentage change in the length? So in this case, for the larger this thing, so this is going to be for the case of a ductile material, this is for the case of a brittle material. Then for another measure, this is again for your information, another ductility measure is defined as percentage RA. So like the length is changing, keeping the volume constant, there is also going to be a change in the area taking place, right? So the area is going to decrease, right? So as a result, the final area is going to be less than the original area. So we say that A naught is the original area, AF is the final area. So this is the percentage change in the area that is taking place. Further, when you are applying some force on an object to change its dimensions, so obviously that force gets stored in some form of energy, or basically stores some energy. So how much is the energy that is stored? That is also known as the elastic potential energy. So what is elastic potential energy? Elastic potential energy is basically the ability of a material to store energy. So energy is stored best in the elastic region. So if we have to define it, so what will we have? We'll say that UR is basically the resilience or the elastic potential energy, that is defined as sigma into dE. So sigma is nothing but the stress that you have, and E is the amount of change that is actually taking place. So if we assume a linear stress strain curve, so the linear stress strain curve up to this point, right? So up to this point, if we say, so this resilience is going to be, means you just need to integrate this. So if you integrate it, effectively you will get a relation like this. You can also understand that it is a kind of an average value that has been taken in. So this is how do we define the resilience. This is again a definition. Now any object, whether strong or not, how do we define it? There is something known as the toughness of an object. So to define the toughness, you need to identify something known as the energy that is required to break a unit volume of a material. How much is the energy that you need to break a particular amount of material? That is what is known as a toughness. And how can you define it? So you can define it approximate by the area under the stress strain curve. So you have a stress and a strain curve. So here you have stress, here you have strain. So once you take an integration over the stress strain curve, that results into what is known as the toughness of the material. If the object is brittle, brittle fracture, when obviously an object is brittle, so obviously it is going to undergo a brittle fracture, so there is going to be an elastic energy. If there is a ductile fracture, means an object breaks after being ductile, there is going to be elastic as well as potential energy that is going to be stored. So let's try to understand more on this particular curve. So on this curve, we see that for small toughness, when the object is kind of brittle, so you get something like this. So they, after this limit, they break, and so you get a kind of curve like this, and then it breaks down. So this is a kind of small toughness. Large toughness, which in the case of metal, so till it remains up to this point, so this is a fracture point. It breaks here, in this particular case, here it continues to this point. Further, for very small toughness, so kind of reinforced, unreinforced polymers. So in this case, so these are the two cases that we talk about when they have not been reinforced. So these are the cases of you have small toughness, large toughness, and some cases of very small toughness. So the metals lie midway between small toughness and very small toughness, right? So this is a curve which tells you about how strong that material is for your further uses. Okay. Now let's try to take up some examples. So which one of the following is not a unit of Young's modulus? Let's try to see. Young's modulus is going to be defined as Newton per meter square, or if you define in terms of in CGS units, so it's going to be dyne per centimeter square, right? So Newton per meter obviously is not. Newton per meter square is, dyne per centimeter square is, pascals is also another unit of pressure. So obviously the first one is the odd one out. Okay, toughness of material is equals to the area under. Okay, obviously toughness is going to be defined in terms of the area under the plastic up to the plastic limit, right? Because material is still tough, after the plastic limit it starts breaking down. So obviously then it's no use. So toughness of a material is defined under the obviously elastic and the plastic limit. So both of them. So the option should be the option B. C. Sorry. Hopefully you understood till this part. Now let's try to do some numericals based on this part. So let's continue that in the next part. Yeah, thank you. In this part, we got to know that there are different substances like plastics. So plastics, the linear relationship between stress and strain curve exists for a very short duration. Whereas if we talk about for the case of steel, the fatigue limit appears very later on. As a result, this stress strain curve gives us useful insight in classifying the different substances for the different purposes. Now, we are going to go ahead and try to understand, along with applying a force, external mechanical force, along with that, if we say that we apply something like heat. So when we apply some amount of heat, what is the influence that is produced on these particular substances as a result in our next part.